coming to my talk about deep learning and convolutional neural networks, and it is talk related to AI concepts. So apologies if some concepts are a little bit hard, but I will try to clarify everything in order to put it in the right context in the whole presentation. So I have been working with Scala for more than 10 years, building infrastructures, microservices, building domains, using very functional libraries like CAT, Scala, doing a lot of big data stuff with Spark, Kafka, Cassandra, and a lot of machine learning and deep learning using frameworks like Analytics Suite, TensorFlow, PyTorch. And now I'm currently involved completely in NLP research at the UVA. So talking about deep learning, they are supervised machine learning methods that are built on top of neural networks. They are supervised machine learning methods. That means that you need to give them some knowledge, and they will try to build some equations, some function that to try to codify that knowledge. And it's better to this knowledge, this equation, to map one input training feature, training sample into a specific class. And we expect that this equation generalizes well in another, let's say, datasets of the same domain. So maybe you can think that there are a lot of services that are built on top of neural networks, so you can use automatic speech recognition when you activate the subtitles option of your browser, or when you have your camera and you see a square that when the mobile phone is detecting your face, or natural language processing models that are everywhere, doing tasks related to text summarization, text classification, information extraction, but also projects related with graphs have emerged in the latest 4 or 5 years, and a lot of research have been done in order to give this power of this neural network for using graph problems. So this is the basic building block of a neural network. You can see that it's built of a set of layers. And we have here an input layer, which is responsible of receiving all the training samples that come from the outside, and they are represented as a set of vectors of n dimension. And several hidden layers, which are built of a set of neurons. All of them perform a specific mathematical operation. And as you can see here, these neurons are fully connected. There are connections among them. And for example, you should see here one neuron from the L2 layer. It is connected to all neurons of the previous hidden layer. These connections are parameterized with some WG parameters plus some bias parameters. So in a sense, we have these layers, and also we have an output layer, which actually is the layer who is does the prediction. Okay. If we are talking about classification models, the prediction can be represented as an output vector of dimension key. Okay, and we have here the y hat, which is the distribution of the prediction, and another y distribution, which is the real distribution of the classes of the target dimension. So the layer feed-forward equations that you can see here is all the mathematical operations which are executed in each hidden layer. We have here the set vector, the vectorized representation of a set vector, which is the result of the dot product between the WG parameters by the activation functions of the previous layer, plus a Bayesian star. Then a nonlinear activation function is applied to that set vector, obtaining as a result the vectorized representation of that layer. As nonlinear activation function, we can choose sigmoid function, radius function, or tanh. There are more functions, but maybe these are the most common. So the training equations, we have, as we saw before in the previous slide, the layer feed-forward equation. But also when the neural network does a prediction, there is an associated loss with that prediction. If we are talking about classification problems, we can choose the cross entropy loss function that tries to measure the how similar are two distributions, in this case, the P and Q distributions. So the bigger is this entropy, the most different are these distributions. So the model will try to put or to make similar these three distributions. To do that, what the model does is the gradient calculation, which is the partial derivative of this loss function with respect to the all parameters of the input. And then when the gradient is calculated, there is an await update process that tries to update the whole parameters of the network in order to perform better and to get better in each iteration of the training process. So, what is graphs? I think you may know that graphs is a set of vertices and edges. And well, this data that cannot be represented in an Euclidean space. That means that besides the individual features of each node, a lot of information can come from its neighborhood. And yes, equal training samples could be represented as nodes of a graph. So they are defined, so not only by these individual features, there are a lot of information that can be aggregated and much features can be created by this kind of connections. Graphs can be cycled, weighted. There are a lot of topologies and there are a lot of theory behind these kind of structures, and we will see a little bit about that. And as graph examples, we can see here, for example, a molecule, like caffeine molecule that can be represented as a graph. And you can see here the nodes, which are the atoms, and the connections that can be represented with these chemical bonds. And each node of this molecule has its features, own features, like the charge or the mass, so on. But also we have very, very big graphs, like a social network graph. And for example, you could try to perform some graph classification now in chemistry and some experiments related to drug detection. It is now these kind of models has been implemented in the recent years and with a lot of success. So graph neural networks is neural networks that apply on these kind of structures. And it can be used for task or node classification, and you can use for graph classification. Okay? We have two approaches here. Two approaches. One is the inductive approach, which is most similar when you have a common machine learning project. When you have an inductive model, what you need is the whole information of a graph, and then you try to get a representation codified in your model, and you try to implement that equation in another graph. But there are another approach, which is a transductive. In this case, you don't have that information. You only have a little information of the graph, maybe a 10% or 20% of the nodes. And you apply and you create that model that applies to this small set of features, a small set of nodes, and then the model will get that knowledge and will try to smooth all of this knowledge across the graph using that model and the graph structure to do that. This is the case that we are going to see here in this presentation, transductive model example. So convolutions, when you're talking about convolutions, most of the times you are going to think about image processing in those convolutions or convolutional neural networks had great success in the past, and now they are used in this kind of models with a lot of success. And the most important thing here, the main difference between this kind of model and the previous fully connected layer models is that they use these kind of filters or kernels. These filters, as you see here, are this kind of grids that apply some kind of linear operation to the whole image. Beginning in the small pixels the image, it slides from left to right or from top to bottom, doesn't matter. And this filter is going to be shared across the image. That means that we only have these kind of parameters to extract some kind of a specific feature of the image. Because filters, as long as the network is being trained, they acquired some specialization. For example, they can detect eyes, they can detect boundaries, and so on. And when that happens, filters are shared across the network, and yes, we conduct filters, which means that imagine if you are working with a fully connected layer. If you work with that kind of layer, you will have an input training sample, which are with input with each feature as an input with each pixel of our input feature. So imagine how many waves you will need in that case. So filters reduce the number of these parameters. Then we have another feature, which is the translation invariance. And this translation invariance means that this filter is able to detect eyes in the picture, but no matter if the eyes is in this position, in the top left, on the bottom right. Doesn't matter, it's going to be able to detect this kind of feature of the image. And well, if you, for example, rotate the image, the filter is going to detect some specific part of the image that it is a special site. So this is filters. These are very important things in convolutions. And we may think if we can apply this kind of filters, this kind of technology on top of graphs directly. Well, the answer is no. We can't. We need to do some extra previous transformations to that structures. There are two main approaches, which is one is the spectral-based models that requires that you have to represent the graph in the Fourier domain. This is something that comes from the spectral graph theory, and it's something that is not as straightforward to explain. But I will try to make some analogy with the signal processing. If you take your signal, which is defined in time, and you do the Fourier transform, what you do is take the signal and put in the frequency domain. At that simple moment, you can see how the energy of the signal is distributed across the frequency domain. So you have that representation, and you can decompose that representation in terms of basic modes, which are the sine and cosine signals. And these sine and cosine signals forms a basis in this domain. So this basis, if we come back to the graph world, these bases are going to be the eigenvectors of the Laplacian matrix of the graph. So the Laplacian matrix of the graph is some normalized adjacency matrix that represents the graph. And then when we do with this spectral graph representation, we need to calculate these eigenvectors and its corresponding eigenvalues. So this is something that I recommend you if you are interested in this kind of projects to read all of this theory, because it's very important in convolutions to have the concept what is Laplacian, which is decomposition, and so on. There is another approach, which is a spatial-based model, which does not require to calculate this kind of vectors, but it requires a preprocessing stage in order to get another shape of the graph that allow to perform the convolution. So which is the graph convolutional network intuition? If we have here an input matrix X, which is defined by n nodes by f features, this is going to be our input training dataset, this X matrix. But if we have the adjacency matrix which defines the connections between the nodes, as you can see here an example of the graph, and the first row you can see the position 2 and the position 3. The first row represents the node 1, and you can see the position 2 because node 1 is connected to node 2. And position 3 with another 1 because node 1 is connected to to the node 3. And this matrix is symmetrical. If node 1 is connected to 2, node 2 is connected to 1. Okay? So once we have this matrix and we push this data against or through the network, before getting into the first hidden layer, we are going to apply the convolution. So the convolution here is a very simplex equation, a very simple operation, which is the dot product between the adjacency matrix and the X input matrix. As a result, what we will have here is a new matrix, an N by F matrix, with the aggregations of the features of each node neighborhood. So if one node is connected to 3 or 4 nodes, all the features of these connected nodes are going to be aggregated in this matrix. So that is the most simplest approximation of file convolution that we can do here. But after this convolution, we are going to apply a full dense connected layer, and then we are going to have some parameters that are going to be trained. And this output, the H1 field dense connect layer, is going to be applied with another, or is going to be executed another convolution to this output of this hidden layer. As a result, we will have here that the information that was aggregated in the first convolution is going to be aggregated with the information which is 2 steps far away from the node. So, which we call 2 hops distance. So we are going to collect the information not only for the first level of the connections, we are going to get more information from the second level. And then we use another hidden layer representation, and we are going to give more parameters that are going to be trained, and then we have the softmax, which are going to make some normalization in the predictions in order to get the probabilities of each class of the dedicated domain for that integer example. So the graph analysis model, the spectral graph convolution that we are going to use here is not a simple dot product. It is an equation that comes from a publication of Thomas Kidd and Max Welling, which is a semi-supervised learning method, and as it is a simplification of a spectral graph analysis. So it will use 2 layers of convolution and 2 hidden layers too, and it will collect the information of 2 hops neighborhood. Here, in that equation, we have D, which is the degree matrix, which is the number of connections of each node of the graph. It's a matrix, a diagonal matrix. And we also have here the A hat adjacency matrix, which is the adjacency matrix plus the identity matrix. So we are adding the self-connections, the self-connection of each node to that adjacency matrix. So as we told you before in other slides related to the spectral graph convolution, I said that, well, in this kind of approach, we need to extract the eigenvalues, the eigenvectors, and the eigenvalues of the graph Laplacian. But this process is, the process of extracting this kind of vector is very expensive when the graph is very big. So the approximation of the fast spectral graph convolution tries to avoid this step. So having the Laplacian and the eigen decomposition here, the spectral graph convolution is indicated by the equation that you can see here. Okay, and you see here that this G, which is a function of the filters, a function of the eigenvalues parameterized against theta parameters. But this equation can be represented in an expansion of terms of the Chebyshev polynomials. And with some simplifications, we can see here that that polynomial representation can be represented with this equation, which is the same equation that we saw in the later slide. That is something that we are going to try in our experiment. Well, for the frameworks that we will use to create our experiment of fast spectral convolution, we are going to use Apache Spark, GraphX if we have to do some graph split process, if we want to get different subgraphs of the graph. SparkML to use the data frame APIs, everything related to read and write the training datasets. And we are going to use the RDD API because this framework that we are going to use, Analytics, uses this kind of data. And we are going to use Rhys to do all the stuff related to the metrics, adjacency matrix transformation, like converting to symmetric metrics and the normalization process in order to get this fast spectral approximation. And for the training process, we are going to use Analytics Soup. And this framework, Analytics Soup, is built on top of Apache Spark. And it uses only the Spark primitives for doing the process. And it doesn't implement its own protocol, and it is very useful when you have very big Spark cluster. You have to apply this kind of models. And there is a paper which describes how this framework works under the hood. But I will say only that this framework, what does is it takes the RDD, and depending on the number of executors that your cluster has, it creates as many partitions of the number of executors, and then it sends the model across the cluster. So each executor does the training process and then calculate the gradients, but there is another synchronization step that tries to put in common all the parameters of the neural network in order to start with another iteration. Because when an iteration starts, every single node has to have the same copy of the weight parameters. So if you can read, you want to read how it works under the hood, please take a look to the paper, how it is implemented. And what would be the steps of one experiment of this kind of convolutions of graphs? We have the edges of the nodes of two input datasets. We read the files using some specific Spark API like dataframe, RDD. We have to transform these datasets to tensor datasets. Then we have to build the adjacency metrics. Ask to Spark how many workers do we have, if it is necessary to split the graph, because your graph is so big and does not fit in only one partition. And then the model will start to train in a distributed fashion. Okay? More or less is the common process of this analytics soup or big deal framework, how this works. So the case that we are going to implement in this experiment that we are going to see later is the Cora dataset. It consists in a set of publications which are classified into a set of classes, 7 classes. And the citation network consists of more than 5,000 links. So our graphs will have 2,708 nodes with this amount of links. And how this input, these training samples are represented, we have here in this pink square that each training sample is represented by this row, which is the first row is an ID, and the other position that you can grab with a case class is an array of floating point representation that represents if this article contains a specific word. So if one article has a specific one in a specific position, it's because it contains a concrete word, a specific word. Okay, and we also have here the label which this article belongs to. We also have here in this blue square the edges of the node, which are the citations the citations of the connections among articles. When an article makes reference to another article, a new row is included in this dataset. Okay? You can create one case class to grab this edge samples and another case class to grab this train sample. To create the input samples RDD, we take this RDD, element RDD, and we map this RDD and create a training sample. A sample is a specific class of this framework, and it is made by two tensors. One tensor for the features and other tensor for the label. So here we can see that to split this RDD, we could use a Spark custom partitioner in order to get this set of this input training sample in each partition of the RDD. And to create the adjacency matrix, we are going to use Rhys. And as an example, you can see here that Rhys has its sparse matrix representations, because the adjacency matrix will be sparse at the moment. And we can see the operators that this type has, like element-wise addition or element-wise product, and so on. With this framework, you will create, or you will be able to create the representation of that adjacency matrix. And you will be able to create the normalization that corresponds to the spectral graph convolution. So this is the model that we are going to create here. It consists of two convolution layers. The first layer, we also create one dropout. Dropout is a technique that is used in neural networks in order to avoid the overfitting of the neural network. We use a field dense layer, which is in red because it has trainable parameters. We apply a nonlinear Fourier function. We apply another dropout, another convolution, and the final hidden layer with more trainable parameters. And we use a softmax, which is going to normalize the predictions after the logics of the outputs of the previous hidden layer. So as an output, we will have a normalized prediction telling what are the probabilities of each 7 classes for each prediction. So this model here, this type sequential, is from the analytics zoo framework, and it allows calling the add function to add different layers to this sequential. So for the optimization process, we only are going to use 140 samples of the 2,708. Every minibatch is equivalent to one epoch, and one is very important because each iteration we have to take the whole graph to do the convolution, and we have to avoid shuffle because these ML frameworks many times they try to take the input date frame or input date set and try to make shuffle and then sends to the executors. So we cannot do that because we will lose the connection between the graph representation and the nodes. Okay. And what we are going to use here is the cross entropy function using the negative log likelihood criterion and the Adam optimizer with some configuration using a learning rate and the specific parameters of this optimizer. As results of this process, we can see that we only made 1,000 epochs, and we use 140 library samples, and we did two different approaches. We used two different propagation functions. And the first function that we have used here is only the dot product. No, not the dot product. Is taking this component of this spectral graph convolution, we represent that as an identity matrix. So we are not doing any kind of convolution. We are using feed-forward layer, neural network layer without convolution, because this time is going to be the identity matrix. And the other test that we are going to do here is using the spectral graph convolution. So as we can see here, the results of the convolution are much, much better than without convolution. Okay, and we asked to show how the network trains and how that thing could be happening inside the neural network. We are going to take some snapshot of the previous, the last hidden layer, which are a set of seven activation units, and we are going to apply some dimensionality reduction in order to put these 7 activation units in a bi-dimensional axis, applying some technique of dimensional reduction like DSNA. Okay, every 200 epochs of the network, at the snapshot is going to be taken a photo of this internal layer, and we are going to see how different is the training phase when we apply convolution and when we apply a normal feed-forward layer without any kind of convolution. So this is a small video that I did, and we can see here how in each iteration, each 200 epochs, how the network is trained. Okay, so I will try to less speed in the reproduction in order to see better. So here we have the points of this photograph, of this video. Each point here represents an article, and the color represents the class that the article belongs to. Okay, so the network is going to try to put the same colors in the same place. So it's going to collect the red nodes and the red points, and it's going to try to put in the same part of the image. As you can see here, with no convolution, we have a set of red nodes maybe here, but we see that these red nodes are totally dispersed around the graph. And we can continue with the training to see how the network evolves and to see if it's able to put these nodes in the same place of the same class. And we see here that the blue nodes maybe maybe can collect the blue nodes in one part of the image. And we have here some specific point with more red points. But if you see the other classes, they are everywhere. So we are going to leave the network train 200 epochs more to see if the training process improves. And now here we can see that maybe the blue points are concentrated here, and the pink nodes more or less here, the red nodes more or less here. So the first impression here is that without convolution, the network is not able to distinguish which is the class only with the specific words that each article contains. So this is something that we can appreciate here, and we can see that the network does some kind of rotation of the weights. So trying to put all of the nodes in the same part, all of the nodes that belongs to the same class in the same part. Here is the 1000 epoch, and maybe the blue points are here, and maybe pink points here. Well, more or less it tries to do something, but the results are not good. So we are going to see later how with convolution, how this model behaves. And with convolution, we have the next slide. With convolution, we are going to see here for the first one, we are going to decrease the speed once again. Okay. Yes, this is the first 200 epochs. And you can see that with convolution, the network is able to detect or to create a cluster much efficiently. So we have here the red points well concentrated here, blue points, well, blue points maybe are more spread, but we have here the green points and the brown points. And we are going to follow and to see how the network with the convolution, how these parameters, how evolve that representation. And we can see that it's something that trying to make some kind of a spiral, that representation like if it were some kind of galaxy. And then we see that in that rotation, it's able to collect the points of the same class. It's able to create a cluster much more efficiently than the previous case. So look at here, these green points is well concentrated here, and the red points and the blue points. And then if we 100 epochs more, you see that the rotation is being done. The rotation goes on, and we see here how this green points is almost concentrated here, and so on. So we are going to let the network more 200 epochs and to see how it rotates. And here we have the final epoch. We only did 1000. And this is the final result. We have here these round points well concentrated here, this the green points, and the red points here, the blue maybe. These kind of orange points are not so well concentrated, but it is demonstrated that with convolution, this kind of projects can be improved. They have very good results. So, as conclusions with all of these models, well, the implementation there is conclusions and future work. So convolutions and graphs indeed show promising results in some tasks, and well, if we have these tons of data in our Spark cluster, we can execute this kind of models in terms of our infrastructure. And well, we can we can extract, we can leverage the Spark processing power to perform distributed neural network training. And well, having said that we are working with Spark and Scala, we are able to extract all the Scala environment to get all the Scala ecosystem to access to the big data board. And we are going to examine it, or we are going to test this kind of projects on top of Scala 3, because the new version of Spark supports this Scala 2.13, and that allowed us to create our Scala 3 projects with this kind of models. So the implementation that we can follow here is, well, if you can take a look, is analytics project that performed this Scala implementation, and you can see how it trains with convolution and with no convolution. So something to, if we can, for recap, that can be interesting, is that, well, as I said, if you have a very big graph in your infrastructure, you can try to split that graph, and you can try to using RDD partitioner, for example, and using some frameworks that handles graphs on top of Spark, like GraphX. You can just split your graph, and you can create a specific filter for that can be shared across the subgraphs, and only have one model for a big graph. So having said that, my results with all of these data sets were very good. At the beginning, we are going to work more in another type of convolutions, another propagation functions. But as I mentioned, results are very promising in specific tasks. Even in MLP projects, it's going to be something that we are going to know. We should try to put all of these convolutions to see how the some NLP analysis, some NLP semi-supervised projects can be applied with that indeed this convolution projects. So it's done. So if you have any question related to all of these things, please I'm trying to clarify everything again. Thank you.